something subtle began stirring beyond the edges of what our eyes can see. A quiet flicker, a change in color no one expected. An object, known to astronomers as 3I Atlas, the second confirmed interstellar visitor ever recorded, has begun to shine again. Not dimly, not briefly, but with a sudden, electric intensity that no known physics has yet explained. Its once faint and colorless glow shifted into a striking blue, piercing the darkness with a hue that seems to belong more to imagination than science. Welcome to Science Reshaped, where we drift gently through the mysteries that refuse to stay silent. Before we go any further, please subscribe if you love exploring quiet cosmic enigmas like this one, and tell us where you're listening from tonight. It's always humbling to see minds from every corner of Earth gazing up together at the same infinite sky. Astronomers first noticed the change during what was meant to be a routine observation. The telescopes of the Atlas survey, spread across Hawaii, Chile, and South Africa, had been quietly scanning the heavens when the unexpected happened. The object's brightness began to climb, not gradually, but sharply, its light shifting color in a way no recorded comet ever had. NASA, cautious as ever, classified the event as a rapid outgassing episode. But not everyone agreed. At Harvard, astrophysicist Avi Loeb looked at the same data and saw something more daring, what he called a possible propulsion signature. In his analysis, 3I Atlas wasn't merely venting gas into space. It was accelerating, exhibiting a measurable push inconsistent with ice jets or solar radiation pressure. If true, that would mean something extraordinary. An internal power source. In simpler words, an engine. Soon after, the US Naval Research Laboratory confirmed the strange color transition. Red to green, and suddenly, unmistakably, blue. It was as if the object, nearly the size of Manhattan and racing through space at over 130,000 miles per hour, had reignited. It didn't disintegrate as most comets do near the sun. It survived. It brightened. And now, as it slowly re-emerges, from behind the sun, the question astronomers have tried to avoid since the days of Oumuamua is quietly returning. If this isn't natural, then what is it? Stay close. Let's trace how this mystery began. It started on July the 1st, 2025. The Asteroid Terrestrial Impact Last Alert System, or ATLAS for short, picked up a rapidly moving object in the constellation Sagittarius. Its telescopes, designed to watch the night sky for potential impact threats, noticed something moving far too fast. Initial calculations measured its speed at nearly 58 kilometers per second, or about 130,000 miles per hour. For perspective, Earth orbits the Sun at roughly 30 km/s. Mercury, the swiftest planet in our solar family, moves at around 48 km/s. This newcomer was moving faster than any planet in our solar system. Within just days, data confirmed what astronomers quietly suspected. This wasn't from here. Its orbital path was hyperbolic, a clear signature of an interstellar origin. The object wasn't looping around the Sun as a bound comet would. It was merely passing through, visiting once before leaving forever. They officially designated it 3I Atlas, the third interstellar object ever detected, and the first discovered by the Atlas system. To understand the excitement, it helps to remember its predecessors. The first was Oumuamua, discovered in 2017. A long, cigar-shaped object that tumbled through our solar system without any visible coma or tail. It appeared to accelerate, slightly defying easy explanation, and sparked years of debate about whether it might have been artificial. The second, 2I Borisov, discovered in 2019, behaved more like a textbook comet, complete with a tail, water vapor, and predictable outgassing, but 3I Atlas would soon prove to be neither. Early images from the Hubble Space Telescope, taken while the object was still hundreds of millions of miles away, revealed something odd, a soft, teardrop-shaped halo of dust and gas surrounding what seemed to be a solid, icy core. The nucleus glowed brighter than it should have for its distance from the Sun. Its spectrum showed abundant carbon dioxide, but curiously little water vapor. the opposite of what's seen in nearly every known comet. And then came the strangest part. A jet of material seemed to stretch toward the sun, not away from it. That shouldn't happen. Comet tails always point in the opposite direction of the sun, pushed by solar radiation and solar wind. But here was 3I Atlas, defying one of the simplest, most predictable rules of comet physics. Astronomers began to ask the question no one wanted to say aloud: what exactly are we looking at? To understand why the strange glow of 3I Atlas has left astronomers restless, we have to return to something simple: what comets really are. Because if we can grasp what they should be, we can begin to see why this one seems to break the rules of nature. Comets are often called dirty snowballs, relics from the birth of solar systems. They're made of frozen gases, dust, rock, and organic fragments, material left over from the dawn of planets. When one wanders near a star, the heat begins to whisper through its frozen surface. Ice turns directly to gas, forming a shimmering cloud called the coma, a halo that reflects sunlight and makes the comet visible across vast space. That same solar wind then pushes the gas and dust away, forming the familiar tail, which always streams away from the sun like a thread of smoke caught in the light. That's how comets are supposed to behave. Every one we've studied, thousands of them, follows these same principles, but 3I Atlas does not. When the James Webb Space Telescope turned its gaze toward the object on August 6, 2025, its instruments detected something striking. The spectra revealed an abundance of carbon dioxide, far more than anyone expected, and far less water. There was also carbon monoxide, traces of carbonyl sulfide, and bits of water ice, but the ratios were completely off. In most comets, the amount of carbon dioxide and water is roughly equal, maybe 1:1. In 3I Atlas, the ratio was closer to 8:1, 8 times more carbon dioxide than water. That single measurement changed everything. Such a composition could only have formed in an extremely cold environment, far colder than the edges of our own solar system, perhaps so distant that water never even had a chance to freeze there. Carbon dioxide solidifies at lower temperatures than water, so finding it in such dominance suggests the object came from the outermost reaches of a dying system, a place almost untouched by sunlight. It also means 3I Atlas is ancient, maybe older than our sun itself. Calculations based on its speed and the direction it entered suggest it could be 7 billion years old, possibly more. Our sun, by comparison, is only 4.6 billion. If those numbers hold true, this object began its journey before our solar system was even born. A fragment of an older world drifting through the galaxy for eons, frozen in silence until now. But the deeper scientists looked, the stranger it became. Observations from the Very Large Telescope, VLT, in Chile detected something they didn't expect: a continuous release of nickel vapor from the comet's surface. Roughly 4 grams every second was streaming into space. That alone wasn't impossible. Several comets have shown traces of vaporized metals when heated near the sun. But what came next defied every model. There was no iron. In nature, nickel and iron are inseparable twins. They're born together in the cores of dying stars and scattered across the galaxy by supernovae. Wherever one exists, the other follows. Yet 3I Atlas was bleeding nickel into space while showing almost no detectable iron. The ratio was completely skewed, and it matched something that had never been observed in nature before. It resembled the composition of industrial nickel alloys, specifically a compound known as nickel tetracarbonyl, a substance used in metallurgy on Earth. Artificial, manufactured, engineered. No natural comet has ever shown such a signature. Most scientists hesitated to draw that conclusion. They offered alternate explanations. Perhaps the detection was incomplete, or the iron had condensed differently, or the measurements were biased by viewing angle. But still, the data remained. And for the first time, the idea that this object might be more than a random frozen rock began to whisper through scientific circles. As the months passed and 3I Atlas moved closer to the inner solar system, telescopes around the world watched something even more puzzling unfold. Instead of the expected tail stretching away from the sun, it began to show the opposite, a stream of material pointing toward the sun. Astronomers call this phenomenon an anti-tail, and while it's not completely unheard of, it's exceedingly rare and difficult to explain. Images captured by Hawaii's Keck 2 telescope in mid-2025 showed a narrow jet of carbon dioxide and dust, nearly 10,000 kilometers long, extending straight at the sun. Under normal geometry, such a thing shouldn't exist. Sometimes anti-tails are illusions, the result of viewing a standard tail from an unusual angle. Other times, they're caused by large dust particles that lag behind as the comet spins, appearing to stretch forward as the orbit curves. But in 3I Atlas, the anti-tail persisted across multiple weeks and from several different angles. It was real, not an illusion. Then by September it changed. The anti-tail faded, replaced by a more familiar tail, pointing away from the sun, as if whatever had been pushing the material sunward suddenly stopped. The natural explanation was complicated but plausible. Perhaps at first, the comet's carbon dioxide was escaping so slowly that solar radiation couldn't push it outward effectively, causing gas to accumulate on the sun-facing side. As the object moved closer and heated further, the gas jets accelerated enough for solar winds to sweep them back, creating the standard tail. That would fit with a natural comet, though it required a very specific thermal structure and unusual surface composition. But there was another possibility. One Avi Loeb himself hinted at. If the anti-tail was actually thrust, the deliberate exhaust of a system slowing down as it approached the sun, then the switch to a normal tail could mean the engine had been shut off. It was speculative, and to most astronomers, deeply uncomfortable. Yet it was also the first theory that made sense of everything at once. The strange jet, the timing, the abrupt change. For the first time since Oumuamua, scientists faced a question that seemed to hover somewhere between physics and philosophy. Could this object be moving with intention? By early October 2025, 3 Atlas was racing inward through the solar system, passing the orbit of Mars. And for the first time, we had not just one planet watching it, but several spacecraft already waiting in its path. If the mysteries of this interstellar visitor were ever to reveal themselves, this was the moment. On October 3, 2025, 3I Atlas swept within 30 million kilometers of Mars, its closest approach to any planet during its journey. Every available camera turned toward it. Above the red planet, the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter adjusted their instruments. NASA's Mars Reconnaissance Orbiter pivoted its massive high-rise camera, a system so precise it can photograph objects the size of a dinner plate from orbit. Even the Perseverance rover, resting quietly on the Martian surface in Jezero crater, joined in, programming its Mastcam-Z to scan the sky for a faint moving speck. For the first time in human history, an interstellar object was being observed simultaneously from 2 planets. The ExoMars Trace Gas Orbiter returned the clearest early data. Its sensors captured the comet not as a pinprick of light, but as a visible sphere, a pale, hazy glow surrounded by a faint envelope of gas. Its spectrum matched what telescopes on Earth had already hinted at. A coma dominated by carbon dioxide, with traces of exotic compounds. It looked alive with activity, but quiet, controlled, almost deliberate. The Mars Express orbiter followed with spectroscopic readings of its own. Its Omega and SPECAM instruments tried to measure the gas composition, but the challenge was immense. The comet was faint, the sunlight was harsh, and Mars itself outshone everything around it. Still, even through the noise, there were signs of the same carbon-rich chemistry. NASA's Mars Reconnaissance Orbiter was next. Its high-rise camera, designed to resolve details just 30 centimeters wide on the Martian surface, turned its eye toward the dark. From a distance of 30 million kilometers, that meant it could theoretically detect features tens of kilometers across on 3I Atlas, large enough to tell whether it was smooth or fractured, dusty or metallic. And then, unexpectedly, everything went quiet. In early November, NASA still hadn't released the data. The images existed, stored, waiting. But a US government shutdown had frozen most of NASA's communication and media operations. Scientists continued analyzing in silence, but the public heard nothing. In that silence, speculation began to bloom. Was NASA hiding something? Had they seen structure, edges, angles, geometry that no comet should have? The truth, at least for now, remained locked in the data vaults. Meanwhile, down on the Martian surface, Perseverance tried something bold. For 2 nights, October 1st and October 4th, it captured multiple long exposures of the sky, stacking the faint streaks of stars in an effort to glimpse the interstellar visitor. Later, amateur astronomers on Earth processed those raw frames and found what might have been it, a faint, elongated blur hovering above the Martian horizon, exactly where 3I Atlas should have appeared. If confirmed, it would be the first image of an interstellar object ever taken from the surface of another planet. But even without that confirmation, one thing was becoming clear. 3I Atlas wasn't behaving like a craft under power, nor like a comet falling apart. During its Mars flyby, there were no sudden accelerations, no flickers of instability, no course corrections. It stayed on its predicted path with eerie precision, as if guided only by the pull of gravity itself. To some, that steadiness was comforting, proof that it was natural. To others, it was exactly what made it so strange. Because if this object was truly venting as much gas as its coma suggested, there should have been some measurable push, a subtle deviation, a tiny shift in orbit. Yet there was none. It was as if the comet was compensating for its own outgassing, perfectly balanced. The Mars encounter ended quietly. No fireworks, no fragments, no obvious change. It simply passed, indifferent, stable, and silent. But beyond the calm surface, forces were building. In the weeks ahead, as 3I Atlas curved closer to the Sun, it was about to vanish from view. And what happened during that period, while hidden behind the blinding light of the Sun, would become the most mysterious event of all. By late October, 3I Atlas moved into solar conjunction, directly behind the Sun from Earth's point of view. No ground-based telescope could see it. For almost 2 weeks, the object slipped into invisibility, concealed by solar glare. All anyone could do was wait. But a few instruments didn't need Earth's sky to observe. They orbited closer to the Sun, staring at its blinding halo every day. Among them was SOHO, the Solar and Heliospheric Observatory, which has been watching the Sun since 1995. Its LASCO coronagraph blocks the Sun's disk, allowing it to photograph the space immediately around it, a region where comets sometimes disintegrate. On October 18th, a faint dot appeared in SOHO's field of view. At first, it was just another moving speck among hundreds that pass through its cameras each year. But as days went by, something unexpected happened. That dot began to brighten, and not gently, explosively. By October 29th, 3I Atlas reached perihelion, its closest point to the Sun, at a distance of 1.36 astronomical units, just inside Mars's orbit. At that exact moment, every spacecraft watching it, SOHO, NASA's Stereo, A and B, even the GOES 19 weather satellite, saw the same impossible thing. The object's brightness increased faster than any model could predict. Its light curve rose steeply, far exceeding the power law that normally governs cometary brightening. Most comets follow a rule of 4. Their brightness increases proportionally, to the inverse of their distance to the Sun raised to the 4th power. But 3I Atlas was rising almost at the 7.5 power, nearly double the expected rate. It wasn't just brightening, it was surging. For a moment, it seemed to defy every natural curve we've ever measured. And then, the color began to change again. When 3I Atlas reached perihelion, something extraordinary happened. Its brightness didn't just peak, it changed color. And in that change, a deeper mystery began to unfold. Through the filters of NASA's SOHO and Stereo spacecraft, astronomers noticed that the light reflecting from the object had turned distinctly blue. Not just pale or tinted, but vibrantly blue, like burning gas in the upper atmosphere. It was a hue no comet had ever shown before. At first, researchers thought it might be an artifact, a processing glitch, a calibration error, a trick of scattered light. But every instrument that observed 3I Atlas during those final October days told the same story. The brightness increase was real, the blue hue was real, and together they meant something profound. Normally, when comets grow brighter, their color stays close to sunlight, slightly yellowish, or whitish due to reflected dust. Dust grains scatter light unevenly, favoring longer wavelengths, just as the Earth's atmosphere makes our sunsets orange. But gas behaves differently. Certain molecules, when struck by solar radiation, glow in distinct spectral lines, light emitted at precise colors. Carbon monoxide, carbon dioxide, and cyanide compounds can produce emission bands that glow in blue or blue-green wavelengths. So when 3I Atlas began shining bluer than the sun itself, astronomers knew its brightness wasn't coming mainly from dust reflection. It was coming from gas emission, meaning the object was releasing vast amounts of volatile material. Data from SOHO's LASCO C3 instrument confirmed this. Its readings showed that the light being emitted wasn't just sunlight bouncing off the surface. It carried the clear signature of molecular excitation. The comet was glowing from within its own chemistry. That much could be explained naturally. But then came the question that still haunts the discussion today. Why so blue? The sun's surface temperature is around 5,800 Kelvin, giving off a white light with a faint yellow tint. For anything to appear visibly bluer, it must emit or scatter at a higher energy level than the sun itself, a condition that requires either extremely energetic gases or an internal heat source. And that's what made Harvard astrophysicist Avi Loeb pause. He called the observation deeply surprising, perhaps unprecedented. If the blue color wasn't caused by ordinary gas emissions, he reasoned, then it might be the result of artificial heating, some internal system, perhaps even technological, radiating at temperatures hotter than the sun's surface. It was an audacious idea, and even he admitted it bordered on speculation. But as Loeb put it, if 3I Atlas was radiating energy from within, if it was converting power into light, then we weren't looking at a comet at all. We were looking at a machine. Most scientists dismissed the suggestion immediately. The more conservative explanation was that the intense blue glow came from large-scale gas release, dominated by carbon monoxide and cyanide, both of which fluoresce vividly when exposed to solar ultraviolet radiation. The object, they said, was simply venting gas faster and more energetically than anything seen before. The engine wasn't mechanical, it was chemical. Yet even that natural interpretation left uneasy gaps. The color wasn't just slightly blue, it was bluer than models allowed, brighter than gas alone should have made it. The ratio of brightness to distance was extreme, and the curve of its intensity didn't match the expected thermal profile of sublimating ice. It was as if the object's energy output was responding faster than solar heating could account for, as though it had its own internal trigger. For a time, 3I Atlas defied physics itself, and in that defiance, the imagination of the world began to ignite. If brightness and color were the first puzzles, mass would become the second, and it was just as perplexing. As telescopes continued tracking the comet's position, scientists began noticing a contradiction buried in the math. Every active comet, when venting gas, experiences a subtle non-gravitational acceleration, a small nudge caused by the jets of escaping material. It's like the recoil of a miniature rocket engine. We saw it clearly with Oumuamua, whose slight acceleration couldn't be explained by gravity alone. That acceleration, in fact, was one of the reasons Loeb first suspected an artificial origin back in 2017. But 3 Atlas behaved differently. Despite showing a massive active coma, despite venting enormous amounts of gas, it showed no measurable non-gravitational acceleration at all. Its path was perfectly gravitational, as if the sun's pull were the only force acting upon it. That made no sense. If gas was escaping, it should have caused some deviation, even a small one. The fact that no deviation appeared suggested one of two things. Either the object's mass was enormous, or its thrusts were so evenly balanced that they cancelled out completely. Neither option was easy to believe. Harvard's Loeb ran the numbers. Using the observed gas output and the trajectory data, he estimated that the object's total mass had to be at least 33 billion tons. That would make it vastly denser than any known comet, nearly 3,400 kilograms per cubic meter, heavier than solid rock. Typical comets, fluffy mixtures of ice and dust, average only around 500 kilograms per cubic meter. By that standard, 3I Atlas was closer to a metallic asteroid than an icy nucleus. So here was the paradox. If it was truly that dense, it shouldn't be venting like a comet. But if it wasn't venting, it shouldn't have a coma at all. Two realities that couldn't exist together, yet somehow both did. Some tried to reconcile the data. Maybe the nucleus was larger than estimated, spreading its mass across more volume. Maybe only a small region on its surface was active, producing outgassing too minor to shift the orbit. Or maybe, as Loeb provocatively suggested, the entire structure was engineered to maintain perfect balance, compensating for any thrust automatically. It was speculation, yes, but the numbers left too much unanswered to ignore. Between science and wonderby, the time November approached, 3I Atlas had become more than an astronomical object. It was a mirror, reflecting both our science and our imagination. Every new measurement deepened the mystery rather than resolved it. It brightened too fast, it glowed too blue, it followed its orbit too perfectly, and it seemed, impossibly, to carry more mass than any comet its size had a right to hold. As it slipped behind the sun once more, many wondered what it would look like when it re-emerged. Would the blue light fade? Would it break apart under heat? Or would it appear changed, as though something had happened behind the blinding curtain of the sun, where no telescope could see? What came next would push even the calmest scientists toward the edge of belief. As October turned to November, 3I Atlas disappeared behind the sun completely, vanishing into the one place our instruments could not follow. For astronomers, that moment is called solar conjunction, when an object's line of sight passes directly behind the solar disk. It's like a curtain falling, a cosmic blackout. But for those who study the movement of interstellar travelers, it's also the moment of maximum opportunity. Because when an object moves closest to the sun, something powerful happens. Gravity itself becomes a tool. At perihelion, 3I Atlas was traveling at roughly 68 kilometers per second, the fastest point of its orbit. In that instant, any thrust, even the smallest push, would carry amplified consequences. A short burst of energy could alter its entire future trajectory. This is the essence of what physicists call an Orth maneuver. Named after the Greek word for turning point, the Orth maneuver is a fundamental principle in orbital mechanics. When a spacecraft moves through the deepest part of a gravitational well, the closest point to a massive body like the Sun, a single burn produces the maximum change in velocity for the least energy cost. It's how interstellar missions use planetary flybys to slingshot faster or to slow down enough to enter orbit. And that's what made the timing of 3I Atlas so compelling. Its perihelion occurred exactly during solar conjunction, hidden from Earth, invisible to our telescopes, beyond our ability to observe. If ever there were a time for an intelligent craft to perform a course correction unseen, that was it. To a natural comet, perihelion is a trial by fire, the moment of greatest heating and greatest stress. To a spacecraft, it would be the perfect moment to execute a braking burn, to slow down just enough to be captured by the sun's gravity, to remain within our solar system rather than escape into the dark. And that simple question, what if it did, began to divide the scientific community. During that 2-week blackout in late October 2025, all ground-based observatories were blind. Only a handful of space-based instruments, SOHO, Stereo A, and Stereo B, could still see portions of the region near the sun. Their data confirmed that the object brightened, shifted color, and then faded slightly as it passed its closest point. But there was a strange quietness afterward. No unusual radiation bursts, no optical fragmentation, no debris trails, just nothing. If this were a typical comet, that might have been a relief. It survived the heat. But to theorists like Avi Loeb, the silence itself was suspicious. He noted that the alignment of 3I Atlas's orbit with the ecliptic plane, the flat disc-shaped path along which the planets travel, was statistically unusual. Only about 0.2% of randomly arriving interstellar objects would line up that closely by chance. That near-perfect alignment meant the object's path mirrored our own solar system's geometry almost exactly. It wasn't diving in from above or below the plane like most interstellar visitors. It was flying with us, like a guest merging smoothly onto a highway. To Loeb, that geometry was too neat to ignore. It meant that if 3I Atlas did perform any propulsion maneuver while hidden by the sun, the resulting path could easily place it into a bound orbit around the sun, effectively parking it inside our system. Imagine that for a moment. An object from another star, billions of years old, traveling silently through interstellar space, arrives here, slows down, and decides to stay. No direct evidence supported that idea yet, but the timing, alignment, and hidden window all pointed to an opportunity that no natural body would ever consciously exploit, but an intelligent one might. When November began, observatories around the world waited. Teams from Hawaii to Chile, from the Canary Islands to Japan, stood ready for the first re-emergence of 3I Atlas from behind the sun. They wanted one thing above all: trajectory data. If its orbit, after conjunction, matched exactly what gravitational models predicted, then it was natural. If it deviated even slightly, even by fractions of a degree, then something had happened behind the curtain. A thrust, a turn, an Orth maneuver. Astronomers compared it to a detective story written across the stars. The crime scene, the region behind the sun, was invisible, but the evidence would appear later, written in the sky as a change in path. Weeks passed. Then faintly, the first reappearance came. A small dot glowing again in the field of a European solar telescope. It was exactly where the models predicted it would be. No deviation, no unexpected motion. Gravity, and gravity alone, still ruled its path. At least, for now. For those who remembered the strange story of Oumuamua, this moment felt hauntingly familiar. That first interstellar visitor, discovered back in 2017, had shown the opposite behavior: too much acceleration. It drifted away faster than gravity could explain, leading to wild theories about light sails and alien probes. Now, 8 years later, 3I Atlas was doing the reverse, showing no acceleration at all when it should have some. Two interstellar objects, two opposite anomalies, both unexplained, both dancing just beyond the limits of what science could comfortably describe. Some astronomers joked that the cosmos was mocking them, first giving them an object that moved too fast, then one that stayed too perfect. But for the more philosophical, 3I Atlas had become a kind of teacher. It was forcing us to confront not only our understanding of physics, but our assumptions about randomness itself. What if interstellar visitors weren't random? What if some, among the billions drifting through the galaxy, weren't just debris, but the remnants of something once made with purpose? When Loeb published his Black Swan hypothesis, it sent ripples through both academia and the media. He didn't claim certainty, only possibility. He rated 3I Atlas as a 4 to 6 on what he called the Loeb scale, where 0 meant definitely natural and 10 meant definitely artificial. That translated roughly to a 30 to 40% chance of non-natural origin. It wasn't proof. It was a thought experiment, a way to remind scientists not to discard the improbable simply because it was uncomfortable. Loeb's reasoning drew on the cumulative anomalies, the hyperbolic, yet perfectly aligned trajectory, the anti-tail, that turned itself off. The strange composition, nickel without, iron, the unnatural mass to brightness ratio. The blue emission, that outshone sunlight. Each of these alone could be explained away. But together, he argued, they painted a picture that didn't quite fit any familiar category. Others disagreed sharply. NASA's lead small-body scientist, Tom Statler, put it simply: it looks like a comet. It does comet things. It very strongly resembles comets we already know. To most of the community, that was enough. Until data proved otherwise, they would call it what it seemed to be: a comet. Just a very strange one. Yet the divide remained between those who saw an anomaly and those who saw a sign. And as 3I Atlas drifted away from the sun, the debate only deepened. By the end of November, the object had passed the most intense heat it would ever experience. Its blue glow began to soften, its brightness stabilized. The theories quieted down too, replaced by patient waiting for new measurements. Some said the mystery was over. Others believed it had only just begun. Because what if, in that invisible window behind the sun, 3I Atlas really did change course, only slightly, just enough to go unnoticed until months later? What if it wasn't leaving the solar system at all, but slowly coasting into a bound orbit, settling in like a seed that had finally found soil? The answer would take months, maybe years, to emerge. But for now, Earth turned beneath its own soft blue sky, and an object from another star sailed silently through the inner system, trailing secrets in light. By the end of October 2025, the silence around 3I Atlas had turned electric. Every day it was hidden behind the sun. The speculation grew louder. And then, suddenly, the silence broke. Not from NASA or the European Space Agency, but from the internet. A post appeared on a fringe astronomy forum. It claimed that a group of independent radio observers had detected a signal, a repeating pulse at 1,420 megahertz, the same waterhole frequency long favored by SETI researchers as a natural channel for interstellar communication. Within hours, screenshots spread across X, Reddit, and YouTube. Headlines followed. Alien probe 3I Atlas is broadcasting a Fibonacci sequence. NASA caught hiding interstellar transmission. The rumor had everything a viral story needs: mystery, numbers, and a dash of forbidden knowledge. Users claimed the pattern followed the Fibonacci sequence, 8, 13, 21, 34, 55, a mathematical rhythm found in seashells, spiral galaxies, and the code of living things. Others insisted the decoded message read, "Observe, prepare, understand. The gate awaits." It was cinematic, poetic, and completely unverified. Within hours, small SETI-themed YouTube channels uploaded videos with glowing thumbnails and urgent titles. Breaking: alien beacon detected from 3I Atlas. The comments filled with speculation. Was the comet alive? A probe? A warning? A few large science outlets tried to quiet the frenzy, but the digital wildfire was unstoppable. Even respected journalists began asking whether NASA was withholding information during the ongoing government shutdown. The absence of official statements, born simply from closed offices, was reinterpreted as proof of conspiracy. When the scientists stayed silent, imagination filled the gap. Soon, memes appeared showing the comet as a glowing blue eye watching Earth. People pointed their home antennas skyward, hoping to tune in. Live streams labeled "Live Signal from 3I Atlas" gained hundreds of thousands of views, even though they transmitted nothing but static. And yet, under all the noise, the truth was quiet and verifiable. SETI Institute researchers from Green Bank, Allen Array, and Meerkat released brief notes stating the same thing. No structured signals had been detected at 1,420 megahertz or anywhere else. That frequency is constantly humming with neutral hydrogen emission, a natural background tone of the universe. If 3I Atlas had been sending an organized broadcast, multiple observatories would have seen identical patterns at identical times. None did. The data shared online turned out to be recycled from a 2019 SETI training set. Noise altered to look like pulses. Even the waveform plots that circulated on social media were traced to an old graduate-level textbook diagram. There was no signal, no message, no Fibonacci pattern in space, only an imagination. Still, the myth refused to die. For weeks, content creators merged genuine telescope updates with rumor, blurring the line between science and story. And in doing so, they touched a hidden truth about our time. The boundary between discovery and narrative has never been thinner. In a sense, people wanted the signal to exist. After years of distant wars, political noise, and quiet anxieties about our planet's future, the idea that someone else, something ancient, intelligent, and benevolent, might be calling out from the dark felt comforting. Hope disguised as data, even scientists felt the pull. One researcher at the Royal Astronomical Society admitted, "Every time we point an antenna at a mystery, a small part of us wants it to answer back." That longing is woven into every listening array, every silent dish scanning the night. We keep listening because silence itself feels incomplete. In the case of 3I Atlas, the silence held, and that, paradoxically, became its own kind of message. If it were a craft, surely it would communicate. Surely it would reveal purpose. But there was nothing. Just the faint hum of hydrogen, the universe's oldest sound. The absence of transmission became evidence for the opposite view. 3I Atlas was behaving exactly like a comet should. Active, volatile, beautiful, but silent. By mid-November, the viral storm began to fade. Fact-checkers labeled the posts false, YouTube adjusted its recommendations, and professional observatories turned their attention back to what mattered. The physics. Was the brightening continuing? Was the color shifting again? Had the orbit changed? But for the public, the memory of that week lingered. For a moment, millions had believed they were hearing the voice of something beyond the stars, and perhaps that belief itself revealed something profound about us. That in every unexplained shimmer of light, we still search for company. In a universe so vast and mostly quiet, we invent echoes just to feel less alone. In the closing days of October 2025, the sun grew restless. Its surface shimmered with tension, magnetic loops twisting, then snapping, until a storm broke free. A coronal mass ejection erupted from the solar corona, releasing billions of tons of charged plasma into the solar wind. It raced outward at more than 1,000,000 kilometers per hour, crossing the inner system along the very plane where 3I Atlas was then making its closest pass to the sun. The timing was extraordinary. The object was already approaching perihelion, the moment when its orbit dipped nearest to the sun, just 136 astronomical units away, on October 29, 2025. At the exact moment it faced the greatest natural heat of its journey, the sun sent a second wave of energy directly toward it. For ordinary comets, such encounters are catastrophic. A CME can strip away tails, boil surface ice into vapor, even tear a fragile nucleus apart. Astronomers expected much the same fate for 3I Atlas, a fading spark or a final burst of gas before dissolution. But that isn't what happened. As the solar particles reached it, the object brightened. Not briefly, but smoothly, its luminosity rising far faster than models allowed. From the vantage points of SOHO and Stereo A, the light intensified through the final days of October, peaking precisely as the object swung through perihelion. It was as if the storm had not punished it, but awakened it. Scientists on the ground and in orbit worked to explain the phenomenon. The simplest answer was also the most likely. The CME's energy had blasted volatile ices on the surface, triggering a surge of outgassing that made the coma expand and reflect far more sunlight. The color, that faint blue tone first seen weeks earlier, remained, but the brightness curve steepened far beyond expectation. Where most comets brighten with distance following a steady power law, 3I Atlas rose almost twice as sharply. The perihelion light curve, plotted afterward, showed the entire rise compressed within days. A spike in power that could only be explained by sudden heating from the CME's arrival. In other words, the sun's outburst and the comet's flare were likely part of the same event. Still, the steadiness of the glow felt strange. Instead of flickering like dust or debris, the light held firm, unwavering, as though the surface had reached a stable, incandescent equilibrium. For astronomers watching from Earth, that quiet stability was as dramatic as any explosion. 3I Atlas had endured a direct assault from the sun, a literal trial by fire, and emerged intact. No fragments appeared in the coronagraph frames. No debris cloud followed. The object simply passed through the solar furnace and continued on its predicted path, now brighter than ever. In a preprint circulated weeks later, researchers suggested that the CME had temporarily increased the object's activity, releasing hidden carbon-based compounds or metallic dust that enhanced reflection. Others speculated that the flare had stripped away a dark surface layer, revealing a more reflective interior. Whatever the mechanism, one fact stood beyond dispute. The encounter should have destroyed it, and it did not. By the first week of November 2025, the sun quieted again. Its violent pulse faded into background solar wind, and telescopes began regaining a clear line of sight beyond the glare. 3 Atlas re-emerged, glowing steadily in that faint blue hue, its brightness still elevated, its trajectory unchanged. To some, that survival proved nothing more than a resilient comet, dense, solid, stubborn. To others, it whispered of an unknown toughness, something not yet understood in the behavior of interstellar matter. But for now, the data told a simple story. A visitor from another star had passed through the sun's storm and remained whole. It had endured the brightest light a star could offer, and kept its own. And as it drifted back into the night beyond Mercury's orbit, the world waited quietly to see whether that light would fade, or whether it would defy the dark once more. By early November 2025, the sky began to clear. After weeks hidden behind the sun, 3I Atlas slowly emerged again, moving away from perihelion, cooling as it traveled back toward the outer solar system. For the first time since the brightening, Earth's telescopes could see it once more. Night by night, the object rose again in the data streams, a small, steady point of light among the stars. Now the real questions could begin. Would the unexpected brightening continue? Would it plateau or begin to fade? The preprint by Batams and Zhang had predicted the object might remain brighter after perihelion than before, due to enhanced gas release triggered by the solar storm. Over the coming weeks, astronomers would learn whether that prediction was correct, and brightness was only one mystery. Had the trajectory changed? If the path deviated even slightly from the purely gravitational model, it would hint at unseen forces, perhaps natural jets of gas or something less familiar. Teams began new rounds of astrometric measurements, comparing the fresh coordinates against pre-perihelion data, frame by frame. Had the nucleus fractured? Many comets crack apart under thermal stress, a natural response to heating after billions of years in cold space. If 3I Atlas had split, it would confirm that it was fragile and natural. But if it remained whole, even after the CME and perihelion heat, it would imply a structure far more robust than expected. Next came the light. Spectroscopic instruments turned toward the re-emerging glow, separating it into its chemical colors. The analysis would answer one of the key questions of the entire encounter. Had the ratio of carbon dioxide to water changed since perihelion? A shift could mean that solar radiation had excavated deeper layers, exposing new materials, new chemistry, new secrets about its birthplace. But early data hinted at consistency. The same CO2-dominated spectrum, the same faint cyanide signatures, the same relative lack of water vapor that made it so unusual to begin with. Still, scientists knew that light curves tell their own story. As November deepened, observatories began to detect subtle periodic changes in brightness. Most comets rotate as they travel, and these small variations reveal spin rate and shape. If 3I Atlas showed new timing in those fluctuations, it could mean the nucleus had shifted, reshaped, or been altered during its passage by the Sun. If the pattern stayed the same, the object had endured the solar encounter unchanged, another quiet sign of its strength. To coordinate what came next, the International Asteroid Warning Network, IAWN, designated 3I Atlas, a special monitoring target from November 27, 2025 through January 27, 2026. Observatories around the world, in Hawaii, Chile, South Africa, Japan, and Spain, would watch it in parallel, building a continuous record of its position, brightness, and spectral signature. The campaign's goal was simple: refine the methods for studying interstellar visitors, test how quickly the global system could react, and gather as much information as possible before the object faded beyond reach. Every new frame of data would tighten the models of its orbit, its density, its age, and perhaps its origin. Meanwhile, another eye was preparing to watch from afar, far from Earth. The Juno spacecraft, orbiting Jupiter, awaited its own chance to observe. On March 16, 2026, as 3I Atlas would pass within about 54 million kilometers of the giant planet, Juno's cameras and instruments would turn toward it. Though distant, that geometry would offer something no telescope on Earth could. A view from another part of the solar system, different angle, same mystery. That vantage point might reveal surface changes invisible from Earth, perhaps signs of new jets, or a refined estimate of its size and albedo. It would also mark one of the last times the object could be observed before it began its long fade into the deep outer system. Back on Earth, the best observing window was happening right then, mid-November through December 2025. For those with moderate telescopes, 3I Atlas could be seen moving slowly through the constellation Virgo, a faint blue speck among the stars. It was easy to miss if you didn't know where to look, but for those who did, it was witnessing a once-in-a-lifetime sight. An object born around another star, shining briefly near our own. Astronomers watched the data come in, frame after frame. Brightness, position, color, motion, each one a whisper from something unimaginably old, now gliding silently past the realm of Earth. The sun had tested it. The storm had not destroyed it. And now, with the heat behind it and the cold of space ahead, 3I Atlas entered the quiet part of its story, a fading light still under careful watch, carrying the last secrets it would ever share. By mid-November 2025, the first complete sets of post-perihelion data began to arrive. Night after night, telescopes followed 3I Atlas across Virgo, measuring every shimmer of its returning light. The early analyses already hinted at what later December observations would confirm: The brightening had peaked during perihelion and was now holding steady. Rather than fading immediately, the glow plateaued, calm, persistent, and still stronger than before the solar storm. Researchers noted that if this trend continued, it would mean the object had stabilized after its closest pass. Spectroscopic readings taken through late November and into December would show the same result again and again. The carbon dioxide-rich spectrum still dominated. No surge of water vapor appeared, no chemical shift toward ordinary comet behavior. Whatever 3I Atlas had released near the Sun, its composition now looked unchanged. Precise astrometric checks revealed that its path matched predictions. Each plotted point fell exactly on the curve gravity alone could explain. There was no trace of extra thrust or deflection, no sign that solar pressure or hidden forces had altered its motion. Imaging teams also found the nucleus intact. No new fragments appeared, no dust clouds expanded beyond the normal tail. After everything, heat, radiation, the CME's strike, the traveler from another system remained a single solid body. Light curve monitoring through the month refined its rotation period to about 16 hours. A slow, steady spin suggesting balance rather than stress. Nothing in the data hinted at instability. By the end of November, astronomers were beginning to agree. 3I Atlas had weathered its encounter with the Sun unscathed. Its brightness would slowly ease in the weeks ahead, but the story it told was already clear. An interstellar wanderer that had faced the solar furnace and continued on, unchanged, into the deeper dark. By March 2026, the long journey of 3I Atlas reaches its final turning point within our solar system. A quiet meeting with the giant world of Jupiter. For the mission teams guiding NASA's Juno spacecraft, this week carries both pressure and wonder. From March 14 to 20, as the interstellar visitor glides within 54 million kilometers of Jupiter, Juno's instruments will turn outward from the planet and inward toward the Sun, toward the traveler itself. From that distant vantage, geometry becomes revelation. Where Earth's telescopes look outward from the inner system, Juno observes from the outer rim, looking back. The difference in phase angle, the Sun, the comet, and the observer changes everything about the light it sees. How the dust scatters, how the faint halo glows, what shapes hide inside the coma. The spacecraft's ultraviolet spectrograph will search for molecular traces excited by sunlight, tiny flashes that betray composition. It will test whether the comet's carbon dioxide dominance endures as it cools, or if other gases rise in the mix as the surface freezes again. Juno's microwave radiometer, designed for Jupiter's clouds, will listen for the faintest thermal murmur from the nucleus itself. Detecting such heat at this distance will be difficult, the signal almost lost in noise. But if captured, it will reveal the temperature of the surface and help constrain models of the comet's hidden interior. Meanwhile, the visible light camera will attempt high-resolution imaging, perhaps catching fine structure in the coma invisible from Earth's greater distance. The encounter is not just spectacle. Jupiter's immense pull will bend 3I Atlas's path by a measurable degree, and that slight deflection holds answers. By comparing the object's precise position before and after the flyby, astronomers can calculate how strongly Jupiter's gravity acted on it. The result refines one of the last major unknowns: mass. If the path shifts less than expected, the nucleus is lighter than current estimates suggest. If it bends more, the mass is higher. Either way, the numbers will narrow uncertainty and deepen understanding of what this visitor is truly made of. Within the data lies a speculative whisper, not prediction, not belief, merely the acknowledgement of possibility. If, against all reason, 3I Atlas were artificial, then Jupiter would mark its last great turning point before it leaves forever. Any such craft might deploy probes or emit signals here. Yet the scientists themselves call this extraordinarily unlikely. Every observation since discovery has reinforced the natural explanation. A comet, nothing more, though one of unusual endurance. Juno's detectors will record whatever truth passes within view. Electromagnetic spectra, thermal readings, faint images, all gathered from that cold orbit above the Jovian clouds, while far below, lightning flickers across a planet of storms. When the week ends, and the comet drifts beyond Jupiter's reach, the data will join the growing archive of its passage, a final set of measurements before it fades into interstellar night. Gravity will carry it outward, unchanged, its blue glow dimming, its secrets mostly spent. For the observers watching from both Earth and Jupiter, the moment feels less like an ending than a gentle farewell. 3i Atlas came, endured, brightened, and survived. Now it begins the last leg of its journey, away from our sun, back toward the dark between stars. By late March 2026, the data from Juno began to stream home through the Deep Space Network. Each packet carried the faint echo of an encounter that had already passed, a record of light and plasma and silence. When the numbers were translated back into images and spectra, the story they told was calm. There were no anomalies, no radio signals, no hidden acceleration, just the fading light of a comet continuing outward on the course predicted months before. From Earth, telescopes in Chile, Arizona, and Spain kept their gaze fixed on its trail. The glow had weakened, slipping slowly below the reach of small observatories, but the pattern remained the same. Blue tone, stable rotation, predictable motion. It was behaving exactly as a natural body should. By April, its magnitude had dropped beyond easy detection. The observers began to turn their instruments elsewhere, though some refused to stop. They spoke of it like an echo, a traveler that had passed through the sun's fire and returned unchanged. It was, in every sense, leaving home again. The data teams published their final joint summary in early May. The conclusions were simple, almost gentle in tone. 3i Atlas had been a carbon dioxide-dominated cometary body, structurally strong, rotationally stable, and dynamically pure. It showed no evidence of propulsion, fragmentation, or engineered activity. All its changes, color, brightness, tail morphology, could be explained through natural solar processes and gas release dynamics. For most of the scientists who followed it, that ending was satisfying. It left the universe mysterious enough to be beautiful, but not incomprehensible. The comet had answered the questions it could, and kept quiet on the rest. Months later, as it crossed the orbit of Saturn, only the largest telescopes could still see it, a faint mote receding into the dark. Its trajectory would eventually take it beyond the heliopause, out past the solar wind, back into interstellar space. There, it would spend eons drifting in silence, invisible to every eye that once watched it burn. Even in its absence, though, it left something behind, a reminder of how rare these moments are. Twice in human history, we have seen a visitor from another star pass through our system, luminous and fragile, tracing a line between suns. Each one tells the same quiet truth. The universe is wider, older, and far more connected than we ever imagined while looking up from a single planet. So ends the journey of 3i Atlas, not with drama, but with distance. Its glow has gone, but its path remains. A faint scar of light drawn once through the solar wind, now stretching endlessly toward the dark. Long after 3i, Atlas vanished from every telescope. Its name still lingered in conversations and journals, not because it defied the laws of physics, but because it reminded us how rarely we are given a glimpse of something from beyond our own sky. It came quietly, changed nothing, and left, yet in its wake, it reshaped how we look outward. For months, astronomers compared notes, refining orbit plots, and reviewing every spectral trace one last time. Each paper seemed to echo the same sentiment. The universe is generous with mysteries but careful with answers. The object had traveled for millions of years through interstellar cold before sunlight brushed against it again, revealing it to a world that could finally understand what it was seeing. Its visit was a story of survival and proportion, how something as small as a mountain of ice could carry the history of another star, and how the entire solar system, with all its light and motion, could still feel quiet in its presence. Some said it humbled them. Others said it awakened a curiosity that had grown quiet during routine research. Either way, it left its mark not on planets or dust, but on thought. There was beauty in its ordinariness. It did not need to be alien to be extraordinary. Endurance itself was enough. The light it reflected across space became a kind of reminder that exploration doesn't always mean arrival, and that wonder can exist even when mystery dissolves into fact. When the last observation log closed, a few astronomers stayed outside their domes a little longer than usual, letting their eyes adjust to the dark. They knew another interstellar visitor would come someday, perhaps decades, perhaps centuries from now. Maybe that one would behave differently or teach something new. Until then, there was comfort in knowing that the path 3i, Atlas, carved through the void would remain, faint but permanent, in the equations that map our corner of the galaxy. And, as always, each night when we look up, the question remains suspended there with the stars. How many more are out there, drifting unseen? And which of them, even now, might already be on their way? Before we end tonight's story, take a quiet breath and look up if you can. The stars you see now may already be gone, their light still crossing the years to reach you. Somewhere among those invisible paths, 3i Atlas is moving farther from our sun, a faint echo, still gliding through a darkness without horizon. It will never return, and that makes its passing all the more meaningful. If you've enjoyed drifting through this journey with us, please take a moment to subscribe to Science Reshaped. It helps us continue exploring these calm corners of the cosmos, one mystery at a time. And as always, tell us where in the world you're listening from tonight. It's a quiet reminder that even across distance, curiosity connects us all under the same sky. Now let your thoughts slow and your breathing match the rhythm of the night. The universe moves softly, and somewhere out there, 3i Atlas continues its endless flight, silent, steady, and free.